Okay, great. So I see a lot of folks having basic introduction about Python and machine learning. So how many of you have used any deep learning tools like TensorFlow or PyTorch or any other? Okay, TensorFlow, Keras, TensorFlow, great. Okay, cool. So yeah, that's pretty much answers our starting part. So let's begin. I guess we have several people here. So thank you all for joining, and let's start with the session. So before we start and deep dive into the coding section and everything, I'll give you a basic introduction about how this event is going to work and everything. So it's event timelines. So we'll be having four sessions each week, divided into 4 weeks. First one, the today, which is happening now, it's introduction to machine learning and TensorFlow. So I'll be giving a basic introduction about what is machine learning, what is deep learning, and with several other things, and how do we use TensorFlow and Keras, what is TensorFlow, what is Keras. Then in the second week, we'll be having an image classification type using using how do we make computers understand, how do we make computers know about images, how do we help them classify images. It will be all about deep computer vision and how do we implement it using, and that too also using TensorFlow and Keras. The next one would be, in the next week we'll be having a natural language processing event in which we'll be working with text data. In that part we'll be learning about how do we implement text part, like how do we implement natural language processing data, how do we classify, let's say if we have a IMDb review set, or we have something, then how do we predict if the given sentiment, if the given text is a positive review or a negative review, something like that. And the next one is time series prediction, and it will be the wrap up of the event. So in that week, we'll be covering working. We'll learn how to work with time series data, like how do we forecast a weather given the data of previous years and everything. How do we forecast what is the weather gonna be? And we'll also try to predict stock prices and everything working in that environment, working off time series data. And yeah, that's pretty much with it. So in the during the timeline of the event, I'll share some contents, I'll share some books, I'll share some materials which you can refer throughout a month. Try to work yourself out through the codes. uh, Try to understand the basics. I'll give you a basic introduction about things, how do they work, and you can refer the book and the materials which I send you. At the end of the fourth week when we have our time series prediction um, workshop. After that, we'll be hosting an event, or let's say a type of evaluation event. So where I'll be giving type of questions based on all the four types of applications here, which is presented on the screen. And each of you have to, let's say, if you want to participate and if you want to evaluate yourself, you'll have to code it out and submit the solution, and we'll evaluate it according to the results which you produce in the part. So what will happen? Why to join this event? So this event, every participant who successfully completes this event, like let's say he joins all the four events, will have an attendance type short sort of thing. Everyone will be getting a verified certificate of completion by Give My Certificate community. So it's a verified certificate. You can publish it, add it to your resume or LinkedIn. Top 10 participants who complete all the four sessions and implement all the given tasks in the desired time would be given a t-shirt from our side. Top 5 participants will be given a t-shirt and a pad. It's a writing pad and a Microsoft multi-utility pen. And top 3 participants would get a goodie bag. It consists of several things which we have packed, and it's a really a good surprise. So that's all about the introduction part and everything. If you have any doubts, you can ask, or else we'll start with the machine learning basics. Anyone, if you have any doubts, you can ask. All right. So yeah, that's casing. Let's start with the session. So what is machine learning? So anyone of you can unmute yourself and just give a brief explain about what do you understand if you hear the word machine learning. Anything you can type in the chat box or you can speak up. Anything would work fine. Right. No one? Hmm. So let's understand machine learning. What is it is? It's about how we teach machines to learn. How we in a being while being born, like he isn't perfect at all. So we learn from our experience, we learn from several things which we do, and then we become master at it. So that's what it's associated with machines. Machine starts to learn on the given data, like the data is fed into them, and they start to recognize the pattern, they start to interfere some rules, and then these rules, on the based on these rules, they start to predict, like they start to forecast things which can be done by the machines. So this machine learning is not only limited to forecasting. There's several applications of machine learning. So machine learning is a broader aspect. It's a broad field. So in this part, like you can say that a machine learning can be, all of you must have heard about self-driving cars, or let's say face recognition system. All of you must be using a phone on your device. You must be using a phone, and let's say when you open up the camera and you point it towards an object, you see a bounding box or a square box present around the object. So that's all machine learning. It's an object detection part. So the camera is able to apply some machine learning techniques or deep learning techniques, and then uh, create bounding box around the objects which it is able to classify. So this is what machine learning is basic, pretty much like it's teaching the machines about what humans know. It's everything about how do we teach those things to the machines. So if you are someone who doesn't know much about machine learning, here's our Andrew Ng. If you know about him, he's a famous instructor at Coursera, and he has got several courses. So this is what Andrew Ng has got to say. Don't worry about it if you don't understand. Like it's the pretty much if you do any of his courses, or if you have done it, you must have heard him saying this sentence every time. So like yeah, means not everyone gets the hype about not everyone gets the concept clear at one attempt. So machine learning is a combination of mathematics, combination of algorithms, combination of tools, and then when you compile these together into a box, that's what a machine learning is. So moving to the next part, let's start with a simple example, a traditional programming example. So means how is machine learning different from traditional programming? You must have seen this block brick game. So in which part there's a bar at the below, and we have a ball bouncing through the on the top of the bar. So here's an algorithm which every programmer would write to build out this game. So if ball dot collide means if the ball collides on the any of the bricks are present on the upper half, the brick gets removed. So this is what means how the brick is removed from the part, and then um, we change the coordinates of the ball. Like we have a randomly we multiply some value something to the given coordinates of the ball, and the ball keeps on changing its direction. So this is what a typical programming gaming or something like that would work. It's not nothing at all related to machine learning and everything. So it's all traditional programming. You figure out the concepts, you apply them into your code, you visualize, you do anything with it, and then that's it. That's a program which is working. So let's try another thing. Like I talked to you about time series prediction, predicting stock market prices using machine learning. That can be done using a machine learning model. So let's say what happens in a programming scenario. Like if you code it out in a programming scenario. So we got to get the stock price, we read the price, we read the earnings, and then return the price by earnings. So this is answer is returned from the code. Like it's a rule which we have predefined the rules. We feed into the data, and the data is worked on with the rules, and the answer is returned back. So that's what a traditional programming scenario is. We have a set of predefined rules. We have the data fed into it, and once the computation is done and everything is worked upon, the answer is returned to the user. Now moving into the high level view of traditional programming, as I discussed here, we have rules, we have data, we have a traditional programming. That's the scenario of traditional programming, and we predict the answers, we output the answers. So these are like hard coded rules. If you have an anomaly into your data, or if you have a very disrupting pattern which is present already in your data, the traditional programming hard coded rule won't be able to work its way through it. Like it won't be able to understand what's something, is there something wrong with the data, or is there something which is an anomaly in the data. So limitations. So we have a limitation of traditional programming. Let's understand this using a simple example. Like let's say if everyone must be everyone must be having a Fitbit or something. Like let's a watch, a digital watch which is used to have a fitness tracker or something, uh, something like that. So let's understand this example. Let's understand the example of a person. Like how do we classify, how do we say that in a traditional programming that if a person is running? So we can simply put a equation that if speed is less than, let's say, 4 km/h or something, we can say that the person is walking, else the person is running. So this can be one part. Now imagine a scenario here. How can we say that a person is walking? Again, we have an equation here. If speed is less than 4, it's walking. Else, if speed is less than 12, it's running. Else, if the speed is greater than 12, the person is biking. So yeah, we handle this scenario pretty much good, pretty much well. Now, next, again, we have something. If we have a single person, like just what if the person is just walking? So if we have a part that if the speed is less than 4, the person is just walking. Now there comes a pattern. There comes a question, like how would be able to say that the person is doing some other activity? Like let's say if he's golfing, he's playing golf or something like that. So traditional programming scenario won't be able to classify this. Like there are no set of hard coded rules which would predict that this person is golfing. Just like we are humans, we are through our naked eyes we can see that that's a picture of a girl playing golf. But how does a machine understand? How does a hard-coded machine algorithm understand that how the person, the data which is fed to it is of a person playing golf? So yeah, that's the traditional programming part which we have done. From programming to learning, now now let's transition from hard-coded programming to some rule-based programming. So just what we saw in the previous slide, we had data, we had rules, and then we had answers. So that was the previous part of how did traditional programming works. Now let's change these axes to flip the axes of the answers and rules. What we do in machine learning is we feed in the data, we feed in the answers, and then we produce rules which would be applied to every part, every data which we had. So like let's say we have weather forecast data. So we feed in the data and we also feed in the weather which was present on that given day. So what does the machine learning algorithm do is it tries to learn through this data. It tries to find out a pattern. It tries to look at the similarities and dissimilarities which is present in the data, and then it produces some rules. So these are the rules which are called as a model. This is a model which has some of its algorithm, some application inbuilt in it, and then these rules are applied every time you want to have some output through the data. So yeah, so that's what it is. Now from coding ML to gathering and labeling data. Now let's say how do we do this? Machines understand only numbers. So like if you feed something a text to it, it won't be able to understand this. It only understands a binary digit or something like that. So what we do is we take the data, we convert it into some numbers, like crunch it down into several huge numbers. Like let's say if this is the person, if here's the figure of a person walking. So we code out, like we produce let's say n cross n matrix, and the matrix has a zeros and ones labels of showing that how the data, how the person walking would look like. So that's the data of a person. walking, that's the data of a person running. Look, you can see that there's some difference between those data, like the ones and zeros are different. And you can see that at the end, the person playing a golf has some other interference, has some other pattern in the data. And this is the input data, like this is the data which we are feeding to it. And the next is we also provide a label of the data. Like if the person is walking, then we have to specify that, yes, this pattern belongs to a person walking. The other patterns belongs to a person who is running. So the machine keeps on understands these patterns, it keeps it in memory. And then when you try to predict things, like let's say if you feed into a data of a person playing a golf, the machine would be able to pretty much able to identify that, yeah, this person is playing a golf. He has a stick in his hand, and he's swinging it, and he has the legs positions are apart, are not very apart in the case of running, but yes, some apart while playing a golf and something like that. So that's what machine learning is, when you try to classify things into a broad spectrum and say that what is machine learning. So machine learning is a combination of maths and algorithms. There are some, like let's say, you must have heard about several algorithms, but machine learning algorithms are somewhat different from basic standard algorithms, which you have been learning in DSA and all. And there's a huge application of mathematics. Like if you want to look at the backside of the machine learning, you'd be able to see that it's all calculus and statistics. Statistics is a tool which is used to infer the patterns in the data, and calculus is a tool which is used to recognize pattern. So machine learning uses these two mathematical concepts to produce some algorithms, and these algorithms are able to classify, are able to predict data and everything. So that's what machine learning does. So if you have any questions till now, you can ask me in the chat section, or we'll move next. Okay, no one. All right. Next, let's move to the next slide. So what would be covering in this session? So we'll be using TensorFlow throughout this whole month. Like we'll try to learn what TensorFlow, working with TensorFlow. So what is TensorFlow? So TensorFlow is a is an open source library used for deep learning and machine learning, developed by Google Brains teams. So it's an open source tool, so it's pretty much available to everyone to use freely, and it has a wide spectrum of application. Like people doing research to people starting their career in machine learning can use TensorFlow very easily. And one thing similarity about TensorFlow is that if you're trying to create a simple linear regression model, and if you're trying to create a simple time series prediction model, the amount of code or the type of like the syntactical part of the code which you write would be pretty much same. Like all the structure of the code would pretty much same, and just you'll have to tweak in some values, some parameters, and yeah, that's it. Your model is good to go into several other parts. So why TensorFlow? So TensorFlow has several applications, as you can see here. So it's a very broad spectrum, and of course it's developed by Google, so it's pretty much advanced. So TensorFlow has TF datasets. It's a library where several datasets, pre-built datasets are present here, and you can just import those data into your station, into your working space, and that's it. You're good to work. There's a model design estimator, Keras estimator. You can learn about this. So what does a Keras estimator do is it helps the model to find out the best parameters suited to work to bring out the best result. So what is the best parameter? We'll surely learn about those in the upcoming slides. So, and it has a distributed strategy part. Like if you I'll give you a scenario, like if you have a very huge amount of data, like let's say 20,000 images to crunch down, and you do not have a GPU present on your system, or let's say if your system is not of very high specifications. So what would happen that your system, once you start to train your model on your system, it would start to freeze, because the amount of resources required by those algorithms running on a system is very high. It's high. It requires very high computation power to crunch down those large pixels into numerical values. So what TensorFlow has is it has a distributed strategy system. Like you can either use a single CPU. Like if you want to do a simple classification problem, a single CPU would be enough. But if you are working on a image classification problem, that would require a very huge amount of compute power. And if the data is very huge, you would also require to transfer your workloads on several of the other components. Like if you have a, let's say, 4 gigabytes of graphic cards on your system, so you'd want, but that even that 4 GB is not enough. So what you'd like to do is you want to distribute the workload. Like let's say if I have if I have a demand of 6 GB of GPU, and I have two 4 GB of graphic cards, what I can do is I can divide the workload of 3 GB on one card and the other 3 GB on one card. So that's what distribution works on. Distribution strategy works in TensorFlow. And the other part is analysis, TensorBoard. The TensorBoard helps us to. Sorry, someone there. Okay, sorry. So TensorBoard helps us to visualize our data as well as the model which we have trained. So data can be visualized by other tools like Matplotlib. Uh, there are other parts. There are several other visualizing tools, Power BI and everything like that. And those are very much useful to visualize the data which we are working on. But visualizing the model which you have created, visualizing the hyperparameters that are present in your model. I'll talk about hyperparameters in the upcoming slides, and how to find out the best suitable hyperparameters for a model is what TensorBoard works helps you in. And there's again other thing like called serialization and TensorFlow Hub. So once you have created a model, you'd like to use these models into some other places. So that's what you can save your models in TensorFlow. And TensorFlow Hub is a machine learning garden where you have very much several built-in pre-trained models. Like you do not need to train those models on data. Those models have a very best suited hyperparameters, and they are pretty much good at the work which they are trained to do. And there's other parts and deployment part. TensorFlow Lite is an application on which you can use to deploy models, and this TensorFlow Lite part is also used in Android. Like let's say if you want to create a machine learning model for your Android smartphones or iOS smartphones, or you can also implement these things into an IoT device like let's say Raspberry Pi. So TensorFlow Lite would be the tool which you would like to go with. Or you can integrate your TensorFlow models into your browsers. So TensorFlow JS is a library built on top of TensorFlow. Like it is a JavaScript library. It's pretty much the coding will be pretty much in JavaScript, and it's cherry on top. Like all the distribution part, like today's browsers are so advanced that they're able to work with. They're able to train the model, everything which you have with yourself. So then TensorFlow JS is the tool which you can use to build models in your browser. So moving with the next part. So what is deep learning? Deep learning, now let's say if someone says that deep learning looks something like this, I guess it doesn't look like that. So deep learning isn't the deep in the deep learning doesn't mean that it's very deep, or let's say it's not something like deep or something like that. The deep in the deep learning means like it's all about the layers which we are building in TensorFlow. Now let's say if we have a 3-layered model, I'll talk about layers in the next session. So layers are, let's say if we have a 3-layer model, so that's a very pretty shallow deep learning model. Now let's see if I have a model with 15 layers, 15 series of steps joined together. So this is a pretty deep model. Like it has got some depth, it has got several parameters to learn, and that's what a deep is. So deep can be one model, one layer model, or it can be a several other layers model. So as you can see, the spectrum of deep learning, it's the very small area into the artificial intelligence part. Artificial intelligence is a very broad spectrum, and we're not going to focus on that part. Like it covers several other aspects, and the other broad spectrum is data science, of course. So data science encapsulates all these parts inside itself. The next one is machine learning. So these are, as I told about machine learning, it's like the algorithm with the ability to learn and being explicitly programmed. And deep learning is a subset of machine learning in which artificial neural networks are there. So this is where the deep learning is. It's all about neural networks. It's all about brains. It's nothing much like It's all about neurons. That in our brains we have several neurons, and these neurons helps us to work out the day-to-day aspects in our life. So that's what deep learning is. How does a neural network learn? As I talked about just now, like we have several neurons in our brain. You can see a meme about that. Like, just as a neuron, a neuron in a machine learning and a neuron in a human brain work pretty much same. Like we humans have been able to implement those artificial neural networks into our computer system. So in our brain, how do those neurons work? Now let's say we perceive something through our eyes, and we send these data as electrical data into our brain. These neurons have a specified threshold. So once a data or a given electric pulse crosses this threshold, the data is transferred to the next neuron. So that's how the transmission of data, transmission of senses work in our brain. Similarly, in a given neural network, the working is pretty much same. Like we have several layers built in, and we have several neurons there. As you can see here, W0, W2 means these are all the neurons, a simple neuron, or let's say a perceptron present into a machine learning model. And these neurons have a threshold. Like it has some given value, after which it would be able to pass this data to the next neuron in the output, and next neuron present to it. So once the data is started to fed into the neuron, it has some predetermined weights predetermined weights and bias. So what are weights and bias? A weight is a predetermined value given to a neuron. Like it is like I'll talk about this in the next section, where you'll learn about these weights and bias and what are those. So once these weights and bias are present, once the neurons gets the data, it does some computation, it does some working on it, and then all the neurons produce an output, and this output is sent to the next neuron present. The next neuron again starts to work on those given received data. The data is again worked on by the next layer of neurons. So everything in the neuron is like it's one neuron is associated with working with one single pattern, or let's say one single piece of recognition that the whole machine learning model has to work upon with. So once these data are passed step by step into the next part, an output is made. Now let's say we predicted some output, and we have a very large difference between the output which we predicted and the outputs that the machine should have predicted from the given data which it was fed to it. So once the data is fed into it, once the output is made, the machine evaluates itself. Like it evaluates that how good I am, how good the prediction is, what I made, and what is the prediction that should I have made. So and then again it goes back, like it back propagates from the output layer to again back to the input layer. And in the way of traversing these layers, the machine learning model keeps on tweaking these weights and bias, which is assigned to every neuron, or let's say perceptron present in the neural network. Once these tweaks are made, the neural network again makes a forward pass. Like the machine learning model starts from the input layer all the way to the output layer. It again makes a predictions. It again makes a prediction, and then that's it. That's how it's keeps on evaluating itself. Yes, Karthik, you have any question?
No, I don't have any questions. It's really interesting. Can I contact you personally?
Sorry?
It's really interesting. It's really fun. And can I contact you personally?
Yeah, sure. I'll talk
Yeah,
state about this after we finish the session. Sure.
yeah, sure.
Okay. So, okay, moving next. Now let's getting started with machine learning. Like as I told you, means there's a professor which all of you know about, and he's from the La Casa de Code or Money Heist. You must have known about him. So what if I told you linear algebra is all about matrix? And yes, believe me, if you're working in a machine learning model, there are several times which you'd work with matrix data. Like if you have defined a neural network model, the neural network consists of several matrices, several computations, several cross products, several types of flipping of the matrices, several types of transpose and computation of data, crunching them. And this is all about data linear algebra part. So the linear algebra is how we represent the data, and calculus is how we learn the patterns. So as I stated earlier, this is how the machine learning model always, or a deep learning model always works. Now, moving on to the next part, has a typical machine learning model. As I stated earlier, what does a typical machine learning model work with? Here you can see that we have a three input layer present there. We have a hidden layer, we have an output layer. So this input layer takes in the data. So it is not compulsory that the dimension of the input layer which you specify should be equal to the number of parameters which your data is learning. It is not necessary at all. Like, let's say you can have a 10 neuron layer, first layer, and your data can be having only 2 parameters to learn with. So it's completely true. It's not like that. It's not a hard-coded rule that the number of neurons in the first layer should be equal to the number of parameters that the machine learning model needs to learn. So once the input layer is present, but we do need to specify the dimensionality of the data that is being fed into the first layer. And from there, the TensorFlow keeps on, all the machine learning models keeps on using those data. Then we have a hidden layer. As I told you about, this is a one single layer. We have one single layer of hidden layer present here, and it's a very shallow network. Like we have only one hidden layer present in this part, and then we have an output layer. So hidden layer can consist of several hidden layers. Like we can have around up to any infinite numbers of hidden layers present in the machine learning model. And these hidden layers is where the real magic happens. Like, these hidden layers have an activation function, and have an optimizer, have an learning rate, have several other parameters, have a weight and a bias. Like you can see that, as I told you about earlier, all the neurons have a weight and a bias associated with them. And then next is an output layer. So this output layer must be of the same size of the type of data which we are trying to predict. Like, let's say if we are trying to predict if its given image is of a dog or a cat. So we must have one neuron at the end, and that one neuron should predict that if it's a dog, then I'll output 1, or else I'll output 0. So, but how does this work? In a machine learning classification model, it's the output is always a probability. We know that machines cannot be 100% sure about the data they are predicting. So what they do instead is that they'll output you an array of, like, let's say if you are having an output of 2 data, like a dog and a cat, and the output has to be produced. So you'll get an output, you'll get a 2x1 matrix, and that matrix will be having a probability of the data. Like, let's say if you fed an image of dog into the neural network, the output will be like a probability stating 0.99% that it's I'm a dog, and the next would be, and a probability that 0.001% that it's a cat. So that's how machine learning models work. It's all about probability. They try to predict, they try to pull out a probability of the given data, and how accurately they're able to predict the data with themselves. So yeah, the hello world of machine learning. So now it's time for us to start something with the code and everything. So here's a simple example which I'll be working with, and we'll move on to an IMDb review classification dataset. So I'll talk to it about short in the meantime. So here we have 2 values. As I stated, we need to feed in some data. Like we have an x. X is the parameters that are being fed into the data, and y is the label. Like, y is the output that is associated with a given value. If you can see here that we have, can you infer the pattern which is present in the data here? Like, can you know that, can you infer what's the algorithm it's gonna have if we try to feed it into the model? Like, yes, so we have a numerical data. We'll be crunching it down into a neural network, and then we'll try to infer the pattern. So here you can see that we have X and we have
Is it
Y.
a straight line?
Yeah, sure. Yeah, that's very good. Correct. That it's a straight line model. It's you must have heard about y is equals to mx plus c. That's the equation the line would be forming. Here, w is equals to wx plus b. Why did I light it as wx plus b? Is that here what the model will try to do is, as I told you about, weights and bias. So W is the weight that the model will have, and it will have a bias. So now we'll learn about what is a weight and what is a bias. Weight are some predetermined values that are fed once the neural network is defined. So it's like you have weight. We randomly initialize some values to the data to the neural network, all the neurons, and we specify some amount of bias. Like let's say if a neuron goes all the way to, like let's say the weight of a neuron automatically switches to 0. So that equation part w into x would be 0, and our neuron would be rendered stateless. It won't be able to do anything. So what we do with the bias is that we specify a small amount, very small integer to it. This bias helps to keep the neuron active. Like it helps the neuron to stay alive and not initialize its weight to 0, and thus keeps on contributing to the working of the model. So as you can see from the data that it's and y is equals to 2x minus 1 equation. So 2 times of x minus 1 is equal to the data which we'll be getting through the equation part. Now here's our model which we'll be trying to define. So I'll be coding this in the Google Colab. I guess you all have you know how to open a Google Colab. If you don't, you can just type Google Colab in Google, and just you'll have a Jupyter Notebook environment. Jupyter Notebook is a type of machine. It's a tool. It's an editor which you can use to work your in which basically used in data science and machine learning models. And Colab is an free cloud computing resource provided by Google. Like you have access to GPUs, TPUs, and several high resource and compute power, which you can use freely for 12 hours. So let me walk you through the code first, then we'll go into the working of the part. So we'll import several libraries. Importing TensorFlow is as easy as it can be. Import TensorFlow as TF. We import NumPy, and we import Keras. So what is Keras? Keras is an high-level API of TensorFlow. High-level API, not only for TensorFlow. It's for like using Keras, you write a code once and you can run it on several other platforms. Like you can use TensorFlow as a backend, you can use Microsoft Cognitive Service as backend, or you can use CUDA, or let's say other machine learning libraries developed by Stanford Institute. It's a very old machine learning library, and currently not very many people use it. And so TensorFlow has several parts. So we import from TensorFlow.keras import sequential. So as I stated earlier, sequential is a functional API present in TensorFlow. It's an API which we'll be using to build our model. So a sequential means that we stack layers we stack those layers one over another. So sequential helps us in creating a sequence of the layers which we're trying to build. So that's what sequential is. Sequential does. There's another API in TensorFlow which is called functional API, and it's a very broad spectrum. It's an advanced TensorFlow technique which you can use to build several output models, or let's say if you research about several things, like if you say work on a VGG network or other networks, if you have a model which is trying to predict several other outputs having several other inputs, you can use a functional API. So we built a model. So here we have a dense unit. I have only set one unit, and the input shape is that, just as you saw in the previous part, we only have one X. So that's the input shape we need to specify. And we have one unit of neuron. That's it. And dense means it's density of the net. We are trying to specify the density of the network, or a layer. It's a dense layer which we are trying to build. So that's pretty much the model which we are trying to define. And then we compile the model. Like we specify the tools, we specify the several model needs some work, model needs some evaluation matrix, or several other techniques to help it understand how to infer the data, how to recognize the pattern from the data. So it has, we have an optimizer cost called SGD. It's called as stochastic gradient descent. So what does a stochastic gradient descent do is, uh, it helps the model to, like, let's say we have a very huge curve, or let's say a hyperbolic curve or a parabolic curve, and our model is present, or let's say, I'll give you a simple example. Let's say we are playing a hill climb racing game. All of you must have played that on your mobile phone. You must have seen that in that working, while playing the game, you accelerate your bike and you climb the hill, and when you leave the acceleration, your model starts to your biker starts to go down. Now, let's say if you do not provide an adequate amount of acceleration on the next ridge, on the next climb, the biker won't be able to climb that next ridge. That's what stochastic gradient descent helps the model to work with. It's an algorithm, it's an optimizer that helps the model to find a very, uh, in mathematical term, if we say that the model optimizer helps the model to find a global minima. Consider the hill example. There are several highs and there are several lows, but there must be a point on the given hill that must be the lowest of all. Like the lowest point would be present on the hill. The job of our model is to find that the job of our model is to find that lowest point on the hill. So stochastic gradient descent helps the model to traverse that hill and find that global minima. So here global minima is referred to as the lowest point on the hill. There might be several local minima present on the hill. Those are the several downs which are present on the hill. Those are called the local minima, and the lowest point which our model has to find is called as the global minima. So that's the work of stochastic gradient descent. It makes the model move through the ups and downs and find that global minima. There's again a matrix called as loss. It's called how the model is evaluating the output it has produced to the output which it had to produce. So the matrix which we have specified here is a mean squared error matrix. What is a mean squared error? You must have seen that root under x square minus y square. So this is the matrix. Like if we have 2 points present in the space, and let's say in a x and y space, and we have 2 points present at x1, y1, and x2, y2. So what we do is we try to find out the difference between those, like the present scenario and the output with that must have been predicted. The mean squared error is a matrix that helps the model. Like it produces some output, it calculates the loss it has, and then it tweaks back the weights and bias present in it. And sorry. Okay. So that's what it is. And then we have the data, like we feed in the NP array. Mm. We feed it the x and y values. It has the x value is present and y value is present. And then we call model.fit. We pass in the x value, we pass in the y value, and then we pass the number of epochs. It's the number of times the model will move through forward and backward and while working with the model. So now I'll switch to Colab, and I'll show you the screen. Is my screen visible? Are you able to see the Colab screen?
Yes, it is.
Okay, cool. All right. So this is the Google Collaboratory. This is where you can work with your way. Like you can have GPUs, you can have TPUs. Here you can see that I've connected to a runtime. If you want to change a runtime, you can click on runtime part and then click on change runtime. Here you can see that the hardware accelerator I have selected as none because I do not need it. So, but if you want to, let's say if you want to work with an image classification problem, you can just go on to switch on to GPU, or if you want to use TPU. TPU are called TensorFlow processing unit. So this is a very high level part. This is an advanced model of GPU, and it is used for very high computation. For now, I'll switch to none because I do not need a GPU. I'll say if I have connected to the runtime, and then now I import the libraries. So as I told, TensorFlow as TF, NumPy as NP. So importing several libraries. I'll run the mod code. So once the code is run, here I'm defining the unit. So what I'm here there's a small bit of change from the code which I showed in the slide to the code which I have put here. I have uh, created an object of the dense unit. So this is the unit. This is the part. This is the neuron, as I stated earlier. This is the section where the neurons are present, and we need to learn about what the neuron had learned while while its training part. And the next is that we create a model. Model equals sequential model of the part, and I'm using. I had imported model in parts from the Keras library, and then we compile the model. So yeah, pretty much model we have compiled stochastic gradient descent and mean squared error. And once I run this code, the model is done, and then we click on model.fit. Once I click on model.fit, this whole code, with, as you can see, the code is running. The code is working upon. Everything is being computed and everything is done. So I ran it for 500 epochs, and I guess that was too much for us, because I guess you can see here, I'll show in the starting part. Yeah, our first loss, it's 25. Like the model had a loss of 25 when it started. That's because our random values were initialized to all the weights present in the neuron. We, as of here, we had only one neuron present, so it had a very random weight initialized to it. So the loss was pretty much like it did not had any idea about what the prediction is going to be. Once it started to run through the part, once it started to interfere the data, our loss started to decrease down. Our loss started to come down. As you can see, we had started with 25, and now like it has gone below 0. And after 500 epochs, pretty much you can see here that the loss has become significantly down. Like after, let's say after 500 epochs. Okay. Yeah. Here you can see that our loss has gone significantly down. Like it's in the negative values of tens. So our loss has become very much less while training. And for 500 epochs, you can see that it was pretty much fast. And yeah, that's it. That's how our model got trained. Now let's say we need to predict the value. So the output for the model, according to the equations, must have been should have been value 19. But and you can see that our model is predicting pretty much accurate. Like it's predicting 18.97. So it's very much close to 19. So that's how a model prediction does. Now let's say I'll print out the what the model did learn. What are the weights that the model got here? And you can see here that we, according to the equation which we saw, we had 2x minus 1, right, in the given part. So the x value must have been 1, w should have been 2, and you can see that we have 1.99 here. It's pretty much close to 2. So that's the x which got initialized, and 2x minus 1. The other value should have been close to a negative of 1, and you can see that we have minus 0.99, and it's pretty much close to 1. So yes, we were able to infer the data that the model was able to learn. So next is another code walkthrough, and it's much like we are almost done with the part. So in this part, I'll walk you through a IMDb dataset. It's a dataset which is present in the TensorFlow library. It's a TensorFlow dataset, and it consists of 50,000 sentiments present. Like it has some sentiments written in text, and it has a review associated with it, a sentiment associated with it. Either it's a negative or it's a positive review. So the dataset present in TensorFlow is divided into 25 training data and 25,000 validation data. So if we import some of the libraries, and from Keras datasets, import IMDb. So IMDb is a dataset present in Keras datasets, and you can import that. And we load that data into our model, into our library, using this imdb.load data and the number of words. It goes to 10,000. So number of words 10,000 specifies the number of top number of words, like top 10,000 words which we need to import into our data set. And then we create then we vectorize our data. Like, sorry, it's the part where you can see that it's getting the word index and everything associated with a review, all the data part. Here we reverse the word and we decode the word. So it's trying to do that. And next is that we vectorize the data. So I'll write here what is vectorization. We converting the text data to numbers. So here's what it is being done here. The data is being converted. The text data which is present there is being converted to numbers. So we have sequences, we have dimensions. Means what's the dimensionality we want? We specified here that 10,000. So we have the 10,000 dimensional data, and we are converting all the data into the part. And we do this as like we vectorize our text data, X train and Y train, as we divided our train here, train data, train value, everything, train data and train X. And we are also vectorizing, we are also converting our Y output into an array as an same object which we have as an X, we are also producing the same Y object output. So once we vectorize the data, it's pretty much what your model will need. It's all about numbers, like a vectorization part. A vector would be created associated with all the data present in the IMDb review set. And then we have the model here. So here we can see there's a small change in the model. Like we have a sequential model, and I have built this model whole using Keras. So model.add, we have a 16 neuron input, and we have an activation function ReLU. I'll talk about activation in the convolution neural networks part, where we'll learn deeply about convolutions and what activation helps the convolution in. And here we have specified the input shape. You can see that the number of neurons does not matter, does not depend on the input shape which we are using. We have a 10,000 by 1 input shape, and we only have a 16 neuron input. Then we again have a dense layer, a hidden layer present in it. This is a dense layer which we have, and it is in the middle layer. And then I told you that we have a output layer, which is a 1 neuron output. So why do we need a 1 neuron output? It's because we are trying to predict as is the given sentiment a negative sentiment or a positive sentiment, or let's say it is it negative for 0 and positive for 1. So I'll do this, I'll run this code, and then I'll compile my model. So we have an optimizer. As in the previous part, we saw that optimizer was an SGD, stochastic gradient descent. We have an RMS prop. It's another form of optimizer which can be used, and we have several other optimizer, let's say Adam, Delta, AdGuard, and several others optimizer which can be used in the while compiling the model. Then we have a loss, binary cross entropy. So it's binary cross entropy because we have a binary data. Like we have only 2 labels present. It's called binary because we have only 2 data sets to classify with. Suppose we have more than two outputs to predict, it would be a categorical cross entropy. So categorical stands for let's say we have 5 outputs to be predicted, and this is we have 5 categories of data, and we make it as categorical cross entropy. And how are we evaluating our model? So the evaluation of model is done on the accuracy it is having. Like let's say the amount of accuracy the model has, it will tweak itself according to that. So I'll compile the model here. Once the model is compiled, you can see here that there's another way of compiling the same model. We can do that, like let's say we have a learning rate 0.001. I'll talk about this learning rate in convolution neural network parts. So I'm not using that part. I'm not using this. I'm using this upper layer model, this one. I'm not using the below code. So, and now that we have all the part, we divide our data set into validation data and training data. So once the data is defined, I'll train my model. Partial X train, partial Y train. Epochs, we have 20 epochs. Batch size is 512. So it's a mini batch gradient. So we'll be picking 512 sets of data from the given batch, and we'll train the model once, and then we again move forward. And then we have a validation data. So what does validation data helps in? A validation data helps us to evaluate our model. So this is the data which the model hasn't seen. Like let's say the model trains on the trained data. Once it gets trained, it tries to evaluate itself on the weights on the hyperparameters which it has learned. So once it sees the validation data, it tries to predict the y-val, and it also predicts the loss. So now I'll start the training here. You can see that the training has started, and we have initial accuracy of 0.86. We have an 86% validation accuracy, and we have 64% accuracy on the training data, and we have 86% accuracy on validation data. So the model is clearly overfitting like it's predicting well on the validation later, like it's trying to memorize everything, memorize all the patterns present here. And you can see that soon our model reached 99% validation accuracy on the 20th epoch, but it did not cross. So it had a 99% accuracy on the testing data, but it had an 86% accuracy on the training validation data. So the model is clearly overfitting. So what does overfitting means? That overfitting is that the model is clearly able to recognize the patterns present in the trained data. It is able to route it out. It's able to learn everything in it. But when it comes to predicting, the model gets confused. Like it does not has enough data, enough hyperparameters present with it to evaluate out the unseen data present in it. So now let's plot out the things. Like we'll try to plot out what's present in the data. So here's how the prediction plotting is being done. So I'm trying to predict training and validation loss. So here you can see that we started with the training loss and validation loss at the same time, but the training loss kept on going down while the validation loss kept on going up. Like while the model was trying to predict things, at certain point around, let's say 2.5, after 25 epochs, after 2.5 epochs, our model was not learning anything at all. It kept on routing everything, it kept on memorizing everything, and it did not learn anything new. So that's what, like an 86% accuracy we have. And then let's look at the validation accuracy. You can see again that the validation accuracy became stagnant while the training accuracy kept on climbing. Like it went up to almost 100% accuracy, but our validation accuracy is only stuck about 87 86%. So that's pretty much like our model was kept learning, but that's pretty much well performance for a simple neural network. Like we can say that uh, having only having a single dense layer and not having any other techniques such as convolution neural networks and everything like that, it was pretty much good for our model to work upon. And so I'll move out. If you have any questions, you can ask now. That's what about pretty much about the coding section. If anyone of you have any questions, you can ask. Yeah, this is till where we saw the code and everything. Now, yeah. So next is like we covered pretty much concepts in this today's session, and we learned about using importing TensorFlow, setting up an environment, and how to work with TensorFlow, how to use inbuilt dataset present in Keras or TensorFlow, and how to build our first model. We did things. So yeah, this is what something about machine learning is, and you can see that at this point you know more machine learning than most people in the Silicon Valley. And this is what Andrew Ng says always. If you go through his course, you can see that he always does that. Like if you at the end of every course, he'll speak out this. So what's next? We'll be having. So next would be in the next week, we'll work with image data. So how do we work with image data in TensorFlow? How do we make machines classify images using TensorFlow? So we'll explore some basic computer vision techniques, and the machine will learn to see patterns in picture and identify what's in them. Like let's say if we feed a image of a cat or a dog to the our model, the model will be pretty much able to classify what's there in the model, if it is a cat or it is a dog. Then we'll learn to use convolution neural networks in a model. So a convolution neural network is a technique through which you can extract samples, extract features from the data. And we'll also learn transfer learning technique. A transfer learning technique is like, let's say, as I told you, in TensorFlow Hub, we have several pre-trained models and you do not need to train them. So those models have an stagnant weights and bias. Like they have a pretty much working weights and bias, which will help them to train itself, which would benefit us, and which would take a whole huge resource for us if we start training the model on ourselves. So we learn how to use pre-trained models into our machine learning code, and yeah, that's would be what we'll be doing in the next week. So thank you all, and thank you for joining again. And if you have any questions, you can ask, or we'll be
When will the next class be?
again next Sunday. We'll have the next
Next
Sunday.